Hey folks, welcome back to Chapter 2, Lesson 2B, we'll call it. We are going to learn how to take displacement time graphs and convert into velocity time graphs today. We did something similar at the end of the last lesson, but we were using a data table, like we had taken some data with ticker tape. And in this case, we're not going to do that. We're just going to sort of give you a chunk, or I'm going to give you a chunk of a displacement time graph or a velocity time graph and make you convert back and forth between the two. So here's the first thing we're going to do. In order to convert a displacement time graph into a velocity time graph, and here this is blank, we're going to go through this drill. Here's what we measure. It turns out, and you know this already because we've talked about it, that the slopes on a displacement time graph, remember that slope is velocity. So the slope on a displacement time graph is the same as the height of a line on a velocity time graph. So let me show you what that looks like in practice. Heading up to this displacement time graph, that means we need to take the slopes of these different line segments. There's 4 of them we're going to try. We'll do them piece by piece. So the first one, you have to sort of count, or use the scale, I should say. Don't just count boxes. But this first line segment, you can see it goes up 2 meters in a time of 2 seconds. That means this thing is cruising along at 1 meter per second. So that line has a slope of 1. And that slope is the velocity. That's the speed. Well, technically the velocity, but we'll call it speed too. So on our velocity time graph, that happens for 2 seconds. That means we want to draw a nice flat line segment for the first 2 seconds of this object's trip, and it's just cruising along at 1 meter per second. There you go, nice flat line. Let's try the next line segment. It's a little bit steeper. This thing is sped up. Again, you can sketch a little slope triangle if you need to. You can't just count boxes necessarily. Here we've got a run of 1 second. And we go from 2 up to 4, so a rise of 2. So it's covered 2 meters in 1 second. That's a slope of 2 meters per second. And it does that between 2 and 3 seconds. It's cruising at 2 meters per second now. So on our velocity time graph, between 2 and 3 seconds, this thing is cruising along at 2 meters per second. And if we go back up, we've got from 3 to 4 seconds a horizontal line. That's no slope. That means the object was stationary. It wasn't actually moving for a second. It has no velocity. So on our velocity time graph, we're going to go and draw a nice little flat line segment from 3 to 4 seconds at 0 meters per second. And here's what sometimes students like to do. I like to do this as well, but it's up to you. You have creative control. Instead of just having these floating line segments, a lot of students like to drop little dotted lines down. But again, that's up to you. Now, one last line segment here. We've got a negative slope. I'm going to go put a negative in there right now. This thing is now going to the left or going backwards. Remember, one of the things we want to be able to do is create a little story out of these graphs. So this thing is moving with some backwards or constant velocity to the left. Again, we can do a slope triangle if you want. This is from 4 to 7 seconds, so 3 seconds. And it goes from 4 all the way down to, what's that? Negative 0.5. So it drops 4.5. So if we do a rise over run calculation for this one, negative 4.5 over, whoops. There it is, negative 4.5 over 3, negative 1.5. So this thing's cruising backwards or to the left at 1.5 meters per second, and it does that for 3 seconds. So on our graph here, we're going to go to negative 1.5, and it's going to travel with that nice flat line, constant velocity for 3 seconds. So that's what it looks like to convert from a displacement time graph into a velocity time graph. We do have to be able to work the other way. And I'll tell you what the rules are, and then it won't make sense on this graph because it's already all done. But we'll try out some homework. If you want to convert the other way, if you want to go from velocity into displacement, it turns out what you're interested in is the areas under the velocity time graph. Those become the same as changes in height. And again, I'll show you what that looks like in just a moment. We'll try out worksheet number 2, which is the practice that goes with today. So really what that means is we'll end up finding areas of the different shapes. Like that would be an area, this would be an area. We've got some rectangles here, and then this would be one as well. So we'd find some areas of some rectangles, and then I'll show you how that works in terms of changing the height on your displacement time graph. So let's change gears. Let's grab worksheet number 2. It's in that All Resources folder on the website if you need it. It's this one right here. You can see we're going to convert both ways. We've got a chunk of displacement time graph that we want to convert into velocity, and we do that using slope. I like to put these little reminders for myself. And then going the other way, we want to measure area. So maybe let me do the first couple line segments with you just with the slope. That's usually the easiest for people. So let's go back to this before we check out the area. Let's find the slope of this first line segment. You do have to figure out your scale. You can't just count boxes. So it looks like here we're going up by 1, and on the time axis we're going up by 0.2s. And then on the velocity time graph, I might as well play the same game. Every box is worth 2 on the vertical axis, and the time axis is the same. Everything's still worth 0.2. So if we look at this first slope, it looks like we go up 3 meters in a time of 1 second. So this thing is cruising along at 3 meters per second. And that means we're going to draw a nice flat line segment at 3 meters per second. And it does that for 1 second. So we're actually kind of in between some lines there, but that's okay. Something like that. Cruising along at 3. Now we see a steeper line here, so we know the velocity is getting bigger. Again, feel free to sketch slope triangles if you like. We go from 1 to 1.5 seconds, so that's worth 0.5 seconds. And it looks like we go up 1, 2, 3, 4, 5. 5 meters. So rise over run, 5 divided by 0.5 is 10. So this thing for the next half of a second was cruising at 10 meters per second. So on a velocity time graph, we're going to go from 1 to 1.5 and have a nice flat line segment at 10 meters per second. There you go. Now, the answer key to this is also in the All Resources folder, so check that. I will leave you to finish off the last 3 slopes if that's okay. Let me know if you have any trouble. Get in touch with me. I can tell you that that's a negative slope. And then this last one, we're back to a positive slope. So there's 3 more little slope sections you have to find. But I'll let you try that on your own. What I want to do is show you the area piece. So let's go down here. What we're going to do is we're going to look at some rectangles here to start. Here's the first one. Let's find the area of this rectangle. Remember, rectangles, to find area, it's length times width or base times height, however they taught it to you in math class. It doesn't really matter. So in this case, this is a positive area. And it's positive because the whole rectangle is above the x-axis. So I'm going to put a little positive for myself, and if we play that length times width game, it's worth half of a second, and it's 2, 4, 6, 8. 8 meters per second tall, so 8 times 0.5 is positive 4. Now what that tells us to do on the displacement time graph is it doesn't tell us to go to positive 4. That tells us to go up 4. So positive areas tell you to go up by that many meters, and negative areas tell you to go down by that many meters. So what that means is wherever we left off last, which is right here, that tells us by 3 seconds, we want all these line segments to match up, and make a little mark for myself. that we have to be 4 meters above or forwards from where we left off. So that's going to take us to 1, 2, 3, 4. 4 meters up, which actually puts us at 5 meters. And now we have to figure out what kind of line we're going to draw between those 2 points. On the velocity time graph, a nice flat horizontal line means the object is cruising with constant velocity. And we know on a displacement time graph that constant velocity is a nice straight diagonal line. So we're going to grab our ruler and play connect the dots. So there it is right there. Now we have another area to calculate. This time it's going to be negative. It's this one in here. You can see the whole rectangle is below the x-axis. So let's try this out. Area equals negative something. I'm telling you that it drops 22.5 meters per second. So negative 22.5. And it looks like we're worth 0.4 seconds. 2 boxes, and each box is worth 0.2. So if we grab our calculator, just to make sure we don't make an error here, negative 22.5 times 0.4, negative 9. And this is where sometimes people will say things like, Mr. Heinrich, you screwed up the displacement time graph. You can't go to negative 9. It doesn't even fit on the scale. It only goes to negative 7. But remember that area of negative 9 doesn't mean go to negative 9. That means go down 9 from wherever we left off last. So positive areas mean go up. Negative areas mean go down. Not go to, but just go up and down. So by 3.4 seconds, we have to drop 9 meters from where we left off last. We're at positive 5. That's going to take us to negative 4 right there. And I can tell from this little flat line segment on the VT graph that the thing was cruising with constant velocity. And we know that constant velocity on a displacement time graph is a straight diagonal line. So grab your ruler, play connect the dots. Now let's try this area. We're back to another positive one. You can see this rectangle is above the x-axis. So that's a positive area. And if we play length times width, it's 0.6 seconds by 2, 4, 6, 8, 10. 10 meters tall, so that's an area of plus 6, which doesn't mean go to positive 6. That means go up 6 from wherever we left off last. So by 4 seconds, because that's where this line segment ends, we need to be 6 meters above where we left off, which should take us to positive 2. And this object, nice flat line on the velocity time graph, means constant velocity. And that tells us that we grab our ruler and we make a nice straight diagonal line because constant velocity. Okay, we've got another negative area to catch here. We're in negative land right there, all below the x-axis. Let's see what we're at. Area equals negative. Looks like we dropped 2, 4, 6, 8, 10, 12, 14. And that's in half of a second. Negative 14 times 0.5 is negative 7. Which doesn't mean go to negative 7. That means go down 7. So by 4.5 seconds, we need to drop 7 meters from where we left off, which is going to take us to negative 5. And this is a nice flat line segment down here on the velocity time graph, which means nice straight diagonal line on the displacement time graph. Constant velocity. Now, to finish this thing off, we have a weird shape going on here. We've actually got a triangle now. And it's above the x-axis. It's this one right here. So we have to find the area of a triangle. And you remember this from math class. I have faith in that. Area of triangles is base times height divided by 2. So this goes from 4.5 to 5.5 seconds. So it's worth 1 second along the base. And the height, it looks like, is 20. So 1 times 20 is 20, but then divide by 2 because it's a triangle. That's positive 10. And that doesn't mean go to positive 10. That means from wherever we left off, go up 10. So by 5.5 seconds, we need to be 10 meters above where we left off last, and it looks like we were at negative 5. So now we're going to be at positive 5. And now you have to ask yourself, this is where it gets a little tricky, how are we going to connect these two dots on the displacement time graph? So we have to go look at the velocity time graph. We've got this diagonal line going up here, right there. Remember, that shows you that the velocity is increasing as time goes by. This thing's going faster and faster and faster. And that means acceleration. And remember, another way to say acceleration or a positive acceleration is speeding up. And that means any part of an upward curve. Speeding up is a line that curves up. So what we're going to do to connect these dots is not grab our ruler and play that game. We want to show speeding up, which is going to be some kind of upward curve. Had this been a negative slope, then we would do some part of a downward curve because it would be slowing down. So there's a little twist there. Fun little, I think, game, calculating slopes and areas. Again, the answer key for the last little bit of your first conversion here, this chunk, converting down, you can find that on the website. If you have some trouble with any of this, please let me know. If you kind of sort of get it, we're going to do some more practice on this in a couple of lessons, so don't worry. We'll solidify it and we'll get you crushing this stuff in no time. Have fun. Finish off worksheet 2. Let me know if you need some help.